Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi there, Herman and Corn. So let's talk today about RAID, another very interesting tech subject. I think more associated with high-end computers, very much with servers, but they can be used in workstations. And as you guys know, I have a particular fondness for obscure high-end workstation tech gear. So I'm using, I think, 5 drives in my desktop, and my design or my internal volume, it's an Ubuntu computer, was based upon economic availability rather than what makes any kind of sense whatsoever. In fact, I would say don't copy this design because it's a horrible mixture of NVMe and then 4 SSD drives, different manufacturers, and I think it's actually testament to how robust this technology is that even mixing manufacturers drives and that's, I just want to say for anyone looking at doing this, you probably know this, but the reason that's dumb is that, Herman can correct me, you're going to lose the NV, you're going to slow down to your slowest drive speed, in this case, regular SSD. So you're sacrificing performance for no good reason. But the reason that I have more small drives rather than a few bigger drives is because when you get to the kind of 4 drive level, 5 drive level, I can recall that there's different types of RAID you can do that allow you to survive one drive failure without sacrificing a huge amount of capacity. You can do RAID on as few as 2 disks, but then you have a higher capacity trade-off. But RAID is interesting. I know that there's physical RAID controllers as well, or you can just do what I did, which I guess is a software level RAID. And even within those worlds, there's just a bundle of different types. The mathematics I know are pretty incredible as to how this works. But the idea is that if you have a RAID set up properly with your, let's say, 4 drives, if one drive failed or if you just yank it out of the computer, it will go into a degraded recovery state, but it will be able to build back the whole volume, ideally without any data loss. I haven't yet had a full test because I haven't had drive failure in the time I've been running RAID, but I'd be curious to know if it really works as well as you'd expect it to. Herman and Corn, let's talk about, is it random or redundant? Redundant array of independent disks? Random array? I'm never quite sure. RAID, whatever it stands for in computers.
All right, we are back. I hope everyone is having a good week. We have got a real technical deep dive today, something that takes me back to my first custom PC builds, but with some very modern twists.
Herman Poppleberry here, and I am ready. This is one of those topics where the more you know, the more you realize how much engineering goes into just keeping our data from vanishing into the void.
Exactly. Our housemate Daniel actually sent this one in. He was talking about his current workstation setup here in Jerusalem. He is running this mix of NVMe and SATA SSDs, which he admits is a bit of a Frankenstein's monster, and it got him thinking about RAID.
I love that Daniel is just throwing whatever drives he has into a pool. It is brave, but it is also the perfect starting point for this conversation. He wants to know about the different types of RAID, the math behind it, and whether it actually saves your skin when a drive dies.
And that is the big question, right? Because RAA is one of those things that sounds like magic until you are sitting there watching a rebuild bar crawl across the screen for 48 hours. But before we get to the horror stories, let us lay the groundwork. Herman, for the uninitiated, what are we actually talking about when we say RAID?
So, RAID stands for Redundant Array of Independent Disks. It used to stand for Redundant Array of Inexpensive Disks back in the late 80s when it was first conceptualized at Berkeley, but the industry shifted the naming. The core idea is simple. You take multiple physical hard drives or solid-state drives and you combine them into one logical unit. To your operating system, it looks like one giant, fast, or reliable drive, but underneath, the RAID controller is doing a lot of heavy lifting to distribute data.
Right, and it is all about those three pillars: performance, capacity, and redundancy. Usually you have to trade one to get the others. Let us start with the most basic one, even though it is technically not redundant at all. RAID 0.
RAID 0 is the speed demon. We call it striping. If you have two drives, the controller splits every piece of data in half and writes one half to drive A and the other half to drive B simultaneously.
So, in theory, you are doubling your write and read speeds because you are using 2 lanes of traffic instead of 1.
Exactly. The math is simple. Your total capacity is the sum of all drives, and your performance scales linearly with the number of drives, minus a tiny bit of overhead. But here is the catch, and it is a big one. If you have 4 drives in RAID 0 and just one of them fails, you lose everything. Every single file is effectively shredded because half of its bits are on a dead drive.
I always tell people RAID 0 is called RAID 0 because that is how much data you have left when a drive fails. It is great for temporary scratch space, like video editing cache, but never for anything you care about. Now, on the flip side, you have RAID 1.
RAID 1 is mirroring. It is the purest form of redundancy. You have 2 drives, and every single bit written to drive A is also written to drive B. If drive A dies, drive B just keeps humming along. The system does not even blink.
But the trade-off there is capacity. If I buy two 2-terabyte drives, I only have 2 terabytes of usable space. I am essentially paying double for my storage just for the peace of mind.
That is the tax you pay. But for a workstation, RAID 1 is fantastic for your boot drive. It is simple, there is no complex math involved, and the read speeds can actually be faster because the controller can pull data from both drives at once, almost like RAID 0, though write speeds stay the same as a single drive.
Okay, so 0 is for speed, 1 is for safety, but Daniel was asking about setups with 4 or 5 drives. That is where we get into the more magical math of RAID 5 and RAID 6. This is where my brain usually starts to sweat a little. How do you get redundancy without losing half your space?
This is where we talk about parity. RAID 5 is probably the most famous server configuration. You need at least 3 drives. Let us say you have 3 drives. The system stripes data across 2 of them, but on the third, it stores parity information.
And parity is basically a mathematical summary of the data on the other drives, right?
Precisely. It uses the XOR operation, which stands for exclusive OR. For the listeners who remember their logic gates, XOR is a bitwise operation where the output is true if exactly one of the inputs is true. In the context of RAID, if you have data bit A and data bit B, you XOR them to get parity bit P.
And the magic is that if you lose A, you can calculate it by XOR-ing B and P.
Exactly. The math is reversible. A XOR B equals P. B XOR P equals A. A XOR P equals B. It is beautiful. In a RAID 5 array, the parity is not just on one drive though. It is rotated across all the drives in the array. This is called distributed parity. If any single drive fails, the remaining drives use the parity bits to reconstruct the missing data in real time.
So if I have 4 4-terabyte drives in RAID 5, what is my actual usable capacity?
The formula is n-1 times the capacity of the smallest drive. So 4 drives minus 1 is 3. 3 times 4 terabytes is 12 terabytes of usable space. You'll only lose the capacity of one drive to parity, but you can survive one failure.
That sounds like a great deal. You get the speed of striping and the safety of mirroring, but with a much lower capacity penalty. But I know you have some caveats here, Herman, specifically about what happens when a drive actually fails in RAID 5.
This is the reality check Daniel was asking about. RAID 5 was amazing when drives were 9 gigabytes. But today, in early 2026, we are seeing 30 terabyte HAMR mechanical drives. When a drive fails in a RAID 5 array of that size, the array enters what we call a degraded state. It is still working, but every time you read data, the controller has to do that XOR math on the fly to recreate the missing pieces. Performance tanks.
And then you put in a new drive to replace the dead one, and the rebuild starts.
And that is the danger zone. To rebuild that new drive, the controller has to read every single bit on every other drive in the array. On a 30 terabyte drive, that could take days or even a week. This puts immense stress on old drives that are likely from the same manufacturing batch as the one that just died. If a second drive fails during that week-long rebuild, the whole array is toast.
There is also the issue of unrecoverable read errors, or UREs. I remember reading that with modern high-capacity drives, the mathematical probability of hitting a read error during a multi-terabyte rebuild is actually quite high.
It is terrifyingly high. If you hit a URE on a healthy drive during a rebuild, the controller might not know how to finish the reconstruction, and you end up with a hole in your data. This is why many professionals have moved away from RAID 5 for large arrays and gone to RAID 6.
RAID 6 is just RAID 5 with an extra layer of protection, right?
Yes, it uses double parity. It can survive 2 simultaneous drive failures. The math is more complex, using Reed-Solomon coding or Galois field theory instead of just simple XOR, but the result is that you can lose 2 drives and still be fine. You lose the capacity of 2 drives, but in a world of 30 terabyte disks, that is a price many are willing to pay.
I think it is important to mention RAID 10 as well, because for workstations, that is often the gold standard if you have the budget.
RAID 10 is a nested level. It is a stripe of mirrors. You take 2 drives and mirror them, then take another 2 drives and mirror them, and then you stripe across those 2 pairs.
So you get the massive performance boost of RAID 0 and the security of RAID 1.
Exactly. It is very fast and very resilient. You can technically lose up to half your drives as long as you do not lose both drives in a specific mirror pair. Rebuilds are also much faster because you are just copying data from the surviving mirror, not doing complex parity calculations across the whole array.
Let us talk about the physical versus software side of this. Daniel mentioned he is running an Ubuntu machine. In the old days, you had to buy a dedicated RAID controller card with its own processor and battery-backed cache. Is that still the case?
Not really. For most users, software RAID is actually superior now. In the 90s, CPUs were weak, so offloading the XOR math to a dedicated chip made sense. Today, your CPU is so fast that it can handle RAID calculations without breaking a sweat.
Plus, if your physical RAID card dies, you often have to find the exact same model of card to get your data back. That is a single point of failure that people forget about.
That is a huge point. If you use software RAID like MDADM on Linux or ZFS, you can take those drives, plug them into a completely different computer, and the software will recognize the array immediately. It is much more portable.
You mentioned ZFS. We should probably explain why that is different from traditional RAID, because it is not just RAID, it is a file system and a volume manager all in one.
ZFS is the gold standard for data integrity. Traditional RAID is dumb in a way. It does not know what is a file and what is empty space. It just sees blocks of data. ZFS is aware. It uses checksumming on every single block of data. If a bit flips on your hard drive, which happens more often than you would think due to cosmic rays or hardware degradation, a traditional RAID controller might just pass that corrupted data to the OS.
That is what they call silent data corruption, or bit rot.
Right, but ZFS checks the data against the checksum. If they do not match, ZFS says, wait, this is wrong, and it automatically pulls the correct data from the parity or the mirror and heals the corrupted block. It is self-healing storage. It is incredible.
So for Daniel, who is running Ubuntu, ZFS is definitely something he should look into, especially since he is mixing drives, although ZFS generally prefers drives of the same size.
Yes, that is a universal RAID rule. Your array is only as big as your smallest drive multiplied by the number of drives. If Daniel has 3 1 terabyte SSDs and one 500 gigabyte SSD, a RAID array will treat all of them as 500 gigabyte drives. He would be throwing away a lot of capacity.
It is like a convoy. You can only go as fast as the slowest ship. And in RAID, you can only be as big as the smallest disk.
Exactly. Now Daniel also asked about the performance trade-offs. This is where it gets interesting with SSDs. Back when we used spinning platters, RAID was essential to get decent speeds. But a single modern PCIe Gen 5 NVMe drive can do 14,000 megabytes per second. Do we even need RAID for performance anymore?
That is a great question. For most people, no. A single Gen 5 NVMe drive is faster than almost any SATA RAID array you could build. But if you are doing high-end video editing, like working with uncompressed 8K footage, or if you are running massive databases, you might still want to stripe those NVMe drives.
There is a catch with NVMe RAID though. Often, the bottleneck is no longer the drives. It is the PCIe bus or the CPU overhead. You might stripe 4 NVMe drives and find that you are not getting 4 times the speed because you have hit the limit of how much data the processor can move through the memory bus. Plus, those Gen 5 drives get incredibly hot. Putting 4 of them together requires some serious thermal management.
And there is the latency issue. RAID controllers, especially older ones, can actually add a tiny bit of latency to every operation. With mechanical drives, you did not notice because the seek time of the drive was so slow. But with SSDs that have microsecond latency, the overhead of the RAID logic can actually make the system feel slightly less responsive in some specific tasks.
That is why for most workstations, I recommend RAID 1 for the OS and maybe a large single NVMe for your current projects with a separate RAID array for long-term storage or backups.
Let us talk about the "does it work as expected" part of Daniel's question, because I think there is a huge misconception that RAID is a backup. Herman, how many times have we seen people lose data because they thought RAID was enough?
It is the #1 mistake in computing. RAID is about uptime, not backups. If you accidentally delete a file, RAID will faithfully delete it from all your drives simultaneously. If a power surge fries your power supply and sends a spike into your drives, it can kill all of them. If ransomware encrypts your files, RAID will happily store the encrypted versions.
There is a saying, RAID protects you against a drive failure, but a backup protects you against everything else.
Exactly. And even the drive failure protection is not a guarantee. We talked about the rebuild stress. I have seen arrays where one drive fails, and during the rebuild, the heat and vibration of the intensive reading cause a second drive to fail. Suddenly, your redundant system is a brick.
I think one thing that often surprises people is the right hole in RAID 5 and 6. Can you explain that? It sounds like something out of a sci-fi movie.
It is a bit of a nightmare scenario. Imagine the system is writing data and the parity bit to the disks. The data is written to drive A, but before the parity bit can be written to drive B, the power goes out. Now your parity is out of sync with your data. When the power comes back on, the controller has no way of knowing that the parity is wrong. If a drive fails later, the controller will use that bad parity to reconstruct data, and you will end up with corrupted files.
This is why hardware RAID cards have those little battery packs, right? To finish the writes if the power cuts.
Exactly. Or, if you use software like ZFS, it uses a copy-on-write mechanism that effectively eliminates the write hole by never overwriting data in place. But for traditional RAID 5 on a cheap motherboard controller, the write hole is a very real risk, unless you have an uninterruptible power supply, or UPS.
Which, honestly, if you are running a RAID array, you should have a UPS anyway. It is the best $50 or $100 you can spend to protect your hardware.
Absolutely. Especially here in Jerusalem, where we get those occasional winter power flickers.
Oh, tell me about it. Every time the wind blows too hard, I'm checking my server status. So, Daniel's current setup is a mix of NVMe and 4 SATA SSDs. If he wanted to make the most of that, what would you suggest?
Since he is on Ubuntu, I would tell him to look at ZFS or maybe BTRFs. He could put the 4 SATA SSDs into a RAID 10 equivalent. That would give him great speed and very high reliability. He would lose half the capacity, but for SSDs, the rebuild would be incredibly fast, which minimizes the danger window.
And the NVMe should probably stay as a separate boot and scratch drive. Mixing NVMe and SATA in the same RAID array is usually a bad idea because the whole array will be limited by the slower SATA speeds and higher latency.
Right. It would be like putting a Ferrari and 3 tractors into a relay race. The Ferrari is going to spend most of its time waiting for the tractors to finish their laps.
That is a great analogy. Now let us look at the future a bit. We are seeing things like NVMe over fabrics and specialized storage controllers that handle data at a hardware level in ways that make traditional RAID look like a dinosaur. Do you think RAID has a place in 5 or 10 years?
I think the concept of redundancy will always be there, but the way we do it is changing. In large data centers, they are moving away from RAID and toward erasure coding. It is like RAID 5 or 6, but much more flexible. You can distribute data across hundreds of servers, not just drives. You could lose an entire rack of servers and not lose any data.
It is basically RAID at the network level.
Exactly. For the individual user, I think we will see more intelligent storage where the operating system just manages a pool of drives and you tell it, I want this folder to be mirrored and this folder to be fast. And it handles the block distribution behind the scenes.
That sounds a lot like what Apple does with their Fusion drives, or what Windows does with storage spaces, though both of those have had their share of growing pains.
Storage spaces is actually quite powerful now, but it still lacks some of the robust self-healing features that ZFS has. For a pro workstation, I still think a dedicated Linux-based storage server or a high-end NAS is the way to go.
Okay, so to summarize for Daniel and everyone else, RAID 0 for speed, you do not mind losing. RAID 1 for simple safety. RAID 5 for a balance of space and safety, but be careful with large drives. RAID 6 if you want to sleep better at night. And RAID 10 if you want it all, and can afford the disk tax.
And never ever forget that RAID is not a backup. If you do not have your data in two different physical locations, you do not really own that data. You are just borrowing it from fate.
That is a bit dark, Herman Poppleberry, but it is the truth. Fate has a way of calling in those loans at the worst possible time.
Usually at 3 in the morning when you have a deadline at 8.
Exactly. Well, I think we have covered the basics and then some. This was a fun one. It is rare that we get to talk about XOR logic and file system architecture in the same breath.
It is the heart of the machine, Corn. It is where the math meets the metal.
Before we wrap up, I want to remind everyone that if you are finding these deep dives useful, or if you just like hearing two brothers talk about tech in Jerusalem, please leave us a review on your podcast app or on Spotify. It really helps the show find new listeners who share our particular brand of nerdiness.
It really does. And check out our website at myweirdprompts.com. We have the full archive there, and there is a contact form if you want to send us a prompt like Daniel did. We love getting into the weeds on these topics.
Definitely. We might have touched on some of these themes in our older episodes about data privacy or hardware history, so if you are interested, the website has a searchable archive for you to explore.
Thanks to Daniel for the prompt. I hope your Frankenstein workstation stays healthy, buddy.
Yes, keep those drives spinning, or, well, keep those electrons flowing in the case of the SSDs.
This has been My Weird Prompts. Thanks for listening.
We will catch you in the next one. Peace.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.